Today, we're tackling a problem that challenges us to efficiently determine how many strings from a given list appear as substrings within a larger word. The core challenge lies in avoiding redundant computations when checking multiple patterns. Given an array of patterns in a single word, our goal is to return the total count of patterns that are present as substrings within that word. For instance, if our patterns are ABC, BC, and the word is ABC, we need to find how many of these patterns can be found inside ABC. We're looking for an efficient count. A straightforward brute force approach would be to iterate through each pattern, and for every pattern, check if it's a substring of the word. This involves a nested loop to compare characters. While simple, this can be quite inefficient. If the word has length W and there are P patterns, each of average length L, then each substring check could take up to OWL time. Repeating this for P patterns gives us an overall time complexity of OP*WL. Space complexity is big O of 1, constant time as we don't store extra data. The key insight to optimize this is realizing that we repeatedly check for substrings within the same word. Instead of repeatedly searching, we can precompute all possible substrings of the word once and store them for quick lookups. We'll use a hash set for this. First, we iterate through the word with nested loops. The outer loop picks a starting index, and the inner loop determines the length of the substring starting from that index. For each combination, we extract the substring and add it to our hash set. After populating the hash set with all substrings of the word, we then iterate through each pattern. For each pattern, we simply check if it exists in our precomputed hash set. If it does, we increment our counter. This avoids repeated character-by-character comparisons for each pattern. Let's trace this with word being ABC and patterns ABC, BC. First, we initialize an empty hash set. We start generating substrings. From index 0, OB, ABC. We add these to the set. Next, from index 1, B, BC, add these. Finally, from index 2, C, add this. Our hash set now contains OB, ABC, B, BC, C. Now we iterate through the patterns. O is in the set, count becomes 1. ABC is in the set, count becomes 2. BC is in the set, count becomes 3. D is not in the set, the process completes. The final count is 3. This is correct because ABC and BC are indeed present as substrings within the word ABC, while D is not. The precomputation significantly speeds up subsequent checks. You'll spot this pattern when you need to perform multiple lookups or checks against a fixed set of data that can be preprocessed. If an operation is expensive, but its results are reusable, like checking for substrings in a single word multiple times, consider precomputing and storing them in a hash set or similar data structure for big O of 1 constant time average case lookups. The time complexity is O W squared PL, where W is the word length, P is the number of patterns, and L is the average pattern length. Space complexity is big O of W squared to store all substrings in the hash set. This precomputation trick is a powerful optimization technique. Try the next problem applying this same pattern. Don't forget to like and subscribe for more DSA insights.